Hello everyone, I'm Rafaquat from team Light.AudioVideoSync. In this video, I will give an overview of what I've achieved so far for 3183. Um, so, he, so here's the agenda for the presentation. First of all, I will give an overview of the paper. Then I will share some of my results that I obtained using contrastive and entropy loss, followed by a demo for this method. Next, I will share my results when I did the deepfake detection using contrastive loss only, followed by a demo for this method. Lastly, I will compare the results from both methods. So the paper was published at ACM Multimedia 2020 by Abhinav Dhal and others. So here's how the deepfake detection works. Given a video, it is split into pairs of audio and image segments or chunks. Next, we measure two loss metrics, the contrastive loss and the entropy loss. So what is the contrastive loss? The contrastive loss is measured between each pair and it is the combined loss incurred when measuring dissimilarity in the features extracted after face and scene detection on the video segment and the dissimilarity in the features extracted by speech recognition using MFCC from the audio segment. So there are two modalities that we are targeting, and we are using the dissimilarity. We are actually taking the sum of the dissimilarity of both modalities, and that is our contrastive loss. All right, now for entropy loss. So for entropy loss, we do feature extraction on each audio image segment via face tracking, measuring the loss while doing so, right? And then lastly, we sum the losses for each segment and take the average loss. This is referred to as the modality dissonance score, MDS. So in the paper, the MDS is using both loss metrics to improve the distinguishability between the real and fake videos. So here's the result from the contrastive and entropy loss method. So for testing, I used 20 videos, and 17% of fake videos were predicted as real, and 37.5% of real videos were predicted as fake. And you can see this is the modality dissonance graph that I obtained for this method, and it has a pretty significant intersection near the threshold for the real and the fake videos. So next I will do the demo. So this demo will be using the contrastive and entropy loss. So we will use new test samples, and this is and these two images are screenshots from from my test sample. This is the screenshot from the real video, and this is the screenshot from the fake video. So this is my collab that is using contrastive and entropy loss to do deepfake detection. So in order to run the collab, first you need to download the pre-trained model from this link. So you can just go to the link and you can download the folder. Next, you need to upload it to your Google Drive, and you need to make sure that you upload the model under My Drive folder. So you need to upload it under My Drive folder, which is over here. So you can see this is the My Drive folder, and I've uploaded the model under this folder. If you don't do this, it will throw lots of errors. Then you just need to mount your collab, mount the Google Drive to the collab, and follow the steps below. So first of all, we're just installing some dependencies. You can see I've already done it for the presentation. Next, we will install some more dependencies. So what you might notice that here is a requirements.txt file. So this file, it specifies some dependencies that must be of that version. If we use a different version, it tends to throw lots of errors, right? So that's the reason for putting it in a different cell of code, right? So I've already run this, and you can see the output is here. Next, we need to upload our test video. So there are two folders. There is a test real and a test fake folder. it doesn't really matter whether you put a real or a fake video under test real, or you put a fake or a real video under test fake. You can put whatever videos you want, and the testing output would still be the same. The reason the authors decided to have a test real and a test fake folder is because it's just for us to check whether the video that I'm testing, is it correctly classified as real or fake or not. So that's the main reason. So I've already run this again, and I've already uploaded um, a real video and a fake video. So yeah, so this is the real video, demo real, and this is the fake video, demo fake. So now that we are done with dependencies and uploading videos, we will move on to pre-processing. So since I've already said that this model is pre-trained, so I won't be running the pre-training cell over here, and and uh, I've already uploaded the testing videos, and for that I won't be running the code for testing videos. So I'll just explain what happens in the pre-processing. So this is the stage where the video is split into audio and image segments, and we extract the contrastive and entropy loss from our video segments. So the pre-processing for both of the videos are done over here. Once it's done, we need to train the model based. So since the model is pre-trained, I won't be training it again. You have to run this cell if you want to train it again. Next, I will go to the CSV. So what this code does is it writes the segment paths for the training and testing videos into a CSV. So there are two things that's happening here. The first thing is that there are two splits. There is a train split, and there is a test split all the way at the bottom. So these two CSVs, they appear the same, but they have different meaning. So the train split, it takes for so the information in the train split is that for every video it would take a segment of the video. So in this case, this is the image segment, and then it would take the corresponding audio segment and provide a label. So in this case, this segment of this video, so this segment of this video is labeled as being real. So this is the train split. But if you look at the, so now if we go to the test split, you will see that the test split also has fake labels over here. So this raises a question that we haven't tested anything yet, but there's still a label. The reason there is a label is because the code that later on will read from the train and test split is the same code. It's just referring different files. So to avoid, and so like the CSV they need to be in the same format, and that's the reason the authors decided to have a fake label over here, although it's not a very good decision. So this is the first point for the CSV. The second point is why do we need the CSV in the first place? Because it's causing some issues, some confusion when you look at it. So the reason is when we do the testing, we will consider all the segments that we have, and over here there are 200 videos. So sorry, over here there are 20 videos, and if you think about it, most of them have 10 segments, so there are 200 segments. And it's easier if we can specify the directories in the CSV file, so that the testing code can read it from here and then just refer to the actual directory to get the loss scores for each segment. So that's the second point for this for the CSV. All right, so now we are done with pre-processing. We are done writing the CSV. So now we will go to the interesting part. We will test our detection. using contrastive and entropy loss. All right, so we'll just run this cell. So what you are seeing here is actually the dissimilarity score for every single segment that we have from the pre-processing. So if you look closely, here's our demo file, the demo fake file, and for that demo fake video, this is one segment. This represents one segment, and that segment has a dissimilarity of approximately 297. And if we look even further, there should be yeah, here there's another demo fake segment, and you can see it has a dissimilarity of 289. So so why am I pointing this out? The reason is one of the applications that was mentioned in the paper was that extracting the total loss over each segment of a video, we can actually localize which part of the video was tampered with, right? So we can actually identify that this segment of the video was most likely tampered, whereas this segment is most likely not tampered, right? So the fact that we have different dissimilarity score for different segments, it kind of reinforces that that application is actually possible with our detection model, with this detection model. Yeah. And yeah, there is another segment, and you can see it's 267. So one thing that I should point out is that there is a threshold of 291 score. If the dissimilarity score is above 291, then it's classified as a fake, and if it's below 291, then it's classified as real. So here you can clearly see this segment has a similarity score far less than 291, whereas and then again this segment has a score very close to 291, and if you go above, we have this segment, it has a of similarity score greater than 291. So these outputs, they sort of reinforce that that application is actually possible. All right, so once this all of these are done, you will see an array which just points out all the total loss for each video. So this bit is added by me, and the reason I do it is because later on when I will plot the graph, I will need to take the mean of each of these videos. So yeah, so that's the reason I just print it out and I will write it to a txt file. Okay, all right. So here this is our final result. So when we run this cell, we will get to see which videos are predicted as real and which are predicted as false based on the threshold. So here you can see these videos, most of the videos have 10 chunks or 10 segments. So most of these have 10 segments. Some of them they have 20 segments, and some of them they have 20 segments, and some of them they have 9 segments. So because of all these segments, this is the reason we want to write it to a CSV file in the first place, so that we can easily read it. And this similarity scores that you see here is an average of the total over each of the video segments, right? So yeah, if you look closely, there you can see our demo fake over here has been classified as a fake video, and you can see it has an MDS of 292. So again, I want to sort of emphasize that this value is the least among all the other fake videos. So if you look closely, all the other fake videos, they are well above 291 threshold. And once again, like the fact that we observed that some of the demo fake video segments were real in the previous stage, its MDS, uh, it's the fact that its MDS value is closer to the threshold, so it sort of reinforces the fact that it indeed had segments that are real and segments that are fake. So yeah, the reason I keep on emphasizing this application is because emphasizing this fact is because this is a real application that the detection can provide apart from just detecting it as a fake or not. So it has better utility. Yeah. So now we have our now we have our predictions. So one thing you might notice is that the demo real video is nowhere to be seen, and the reason we will cover that when we go to the section to compare the contrastive and entropy loss. Right. So next I will just run this code to plot the graph, uh, plot the MDS graph, and this is what it looks like. So one thing you might notice is this line over here. It says video wise AUC is 0.611. What this means is the area under the curve, and it means that this area. So you will see. So later on, when we compare the this method with the contrastive loss only method, I will this will make more sense. Like the reasoning behind this graph and the reasoning behind calculating this area. So, so for now, this concludes the demo for the deepfake detection using contrastive loss. So these are the results when deepfake detection was done using contrastive loss only. So the results are still pretty much the same. We have the same false negative percentage. We have the same false positive percentage. The only difference is the MDS graph that we received. Right, and in the next part of the presentation uh, I will discuss why the results are the same but the graph is different. For now I will do a very quick demo of the Google Colab that is using contrastive loss only for deepfake detection. I'll be using the same test samples, and you can see it's the same screenshot as before from the same demo fake and demo real video. All right, so here's the collab that's using contrastive loss only for deepfake detection, and it's the same instructions as before. You need to download the pre-trained model from this link and upload it to Google Drive and mount to Colab. You install all the dependencies the same as before. You upload the test files is the same as before. I've already uploaded the demo fake and demo real. And one thing I wanted to point out is that you will notice the demo fake video has been uploaded to test real and the demo real video has been uploaded to test fake. So this is just to show that there is no difference. There is no difference in even if you swap the uploading as well. Right. So next is the pre-processing for the training and the testing videos. The pre-processing has already been done for the demonstration, and we have already trained the model and we have already run the cell to write the directories for the segments to the CSV file. So now this is the so now we will test the model using only contrastive loss, and well, I've already run this, and you can see the observation that we made before, that some segments of our video was real, some segments of the video was fake. This is also observed much clearer, in fact, when we use contrastive loss only. So for example, if we yeah, over here you can see deep fake, it's below 291, very close but still below 291. Even this one, this value, the similarity score is still below 291, and again this segment has a value greater than 291. So so the fact that the video has real and fake segments is still observed, and it's observed much clearer in over here, right? And if we run it, we will get the same form of output. When we run the final test, we will get the predicted real videos and the predicted fake videos. So you will notice that the demo fake has once again been classified as fake, and this time since we are using contrastive loss only, you will see that the demo real file has also is also showing up over here, and it's been classified as a real video. Right. So next, and you can see one thing is you can see that the video wise AUC, the area under graph is 0.44. So previously when we used contrastive loss and entropy loss, it was 0.61. So this one is significantly less than the other one. So and when we plot the graph, we will see that's the case as well. Yeah, so this is the graph, and the reason it looks a bit different than the one we just saw in the presentation slides is because we just added 2 new videos, so that kind of affected the distribution. But the area is over here is still less than the area that we received when we were using both the loss metrics. Okay, so this concludes the demo for using contrastive loss only for deepfakes. Next, we will discuss the results. We will compare the results from both these methods and yeah, and reach a conclusion. Yep. Okay, so now I will do a comparison of the results that I obtained from both methods. So on the left, these are the false negative and false positive values that I obtained when I used contrastive and entropy loss. And on the right, these are the values that I obtained when I only used contrastive loss. So why are they the same, and why did I do these calculations? So they are the same because we use the exact same set of testing videos for both the methods, and the reason to do this is to make sure that the comparison is fair for both methods. And the second reason uh, is that during detection, both methods had similar dissimilarity scores. So what this means is that for both methods, the real and fake videos, their dissimilarity scores, they weren't exactly the same, but they were within the range of being real and within the range of being considered fake. And that's the reason we have the same classification and same results. However, this is just the first experiment, and this is the reason I'm doing this calculation is because it's part of the experiments that I conducted to verify the claims that the paper makes, right? So so on the surface, the calculations make it look the same, but as we sort of analyze more the outputs based on these claims, we will actually get to see the differences in both of these methods. Okay, so all right, so what's the point of having 2 different methods, one using contrastive and entropy loss and the other using only contrastive loss? So as I said before, this is part of the experimentation itself to verify the claims to the paper. So according to the paper, when both contrastive and entropy loss was used, the graph had a much better distinguishability than using only contrastive loss. However, the experiments that I did contradict these results, and we can look at the graphs and we can deduce a few things. The first thing is that when we're using contrastive and cross entropy loss, the area for real videos is higher and the area for fake videos is lower, and it's the exact opposite when only contrastive loss is being used. So the observation here is that if the video is is likely to be fake, then its dissimilarity score will sort of shoot up, right? It will increase very fast. And why is it that why is the increase so steep? Because when you have a video, and if the audio and the video are not in sync, the difference is noticeable, then the loss is huge. And if the video is tampered, then this loss will naturally be high. And that's the reason why contrastive loss is having such a high area for fake videos. And one more thing is that because the for fake ones they sort of shoot up, the area is high, and because the area is high, the intersecting area over here is actually lower than over here. So over here the area under curve would be 0.442, and over here it's 0.611. So based on the intersection, we can also say that fewer videos that may be fake are classified as real when only contrastive loss is used. So in short, the graph sort of tells us that contrastive loss as of now is better performing than when both are used, than when both loss metrics are used. And so this is one of the first contradictions that I found with the claims made by the paper. So okay, so let's move on. So during the demonstration for the first collab that used both loss metrics, I said that the demo reel was nowhere to be seen. So why didn't it show up? The reason is when contrastive loss was used, it was basically doing a classification. It was basically trying to say if that segment of the video was real or fake. However, for some videos, and for some videos, I mean for this video and for videos similar to this demo reel, it never was the entropy loss was never enough to classify the video as fake or real, and so it was left out. So why wasn't it classified? Why was it left out? Because we did not have enough features to because the model did not have enough features that could be extracted to classify this, right? And so this points out to our training, and I will get to that later on. And this is only observed when cross and entropy, is only observed when contrastive and entropy loss both are used. When only contrastive loss is used, we don't see this. We don't have this issue. So why is it? Because contrastive loss is using the dissimilarity score, and if as long as there is a video and it has the two modalities, it will always take that dissimilarity score, and it always has that threshold of 291. And so and it doesn't depend on that other classification, so it will always distinguish between the two videos, and as a result it provides a better distinguishability than the current than when both of them are used, right? And so this is also one of the reasons why in the previous slide we saw we saw that the intersection area was lower, right? Because it always guarantees to classify it, right? um, Okay, so now this is a limitation. So now I've done experiments for to see how correct the prediction is. I've done experiments to analyze the distinguishability of both methods. So now here's a limitation that applies to both methods as well. So the paper claimed once again that when no audio was present for a given video, the feature extraction from cross entropy would be used to classify it, and in such cases the contrastive loss would be skipped. But upon experimentation, the detection model really fails to do this. And you can see the screenshots over here as well. It clearly shows that the feature extraction is being done on each segment, and when one of the modalities is missing, it throws an error and stops working. So yeah, so the feature extraction doesn't really help when there is no when one of the modalities is absent, right? As for the contrastive loss only model, it still has this limitation because it depends on both modalities itself. So if one of them is taken away, this metric is more or less not as useful, right? Okay, so next, so which of the two models are better? So based on the contradicting results from the previous slide, we can say that contrastive loss is better at distinguishing fake and real videos. So and the only limitation for the contrastive loss is if one of the modalities is absent. Um, Using both methods, however, has a number of limitations itself. As we have seen from the experiments, some videos are skipped because we don't have enough features extracted. In some cases, the inclusion of feature extraction via entropy loss does not come to the rescue for audioless videos because the detection model fails, and no feature extraction is done if there is no if one of the modalities is missing. What it means is that feature extraction, it doesn't it, it is not used to classify, and it's also being used only on the segments itself. So having the feature extraction, with having the feature extraction from the cost entropy loss for detection, just creates unnecessary overhead during pre-processing, because it is not helping in distinguishability. It is not helping when the video has no audio in it. So more or less, removing the entropy loss from the model and using only the contrastive loss is a better model, is a better approach. So with one limitation for contrastive only and four limitations for both models, we can clearly say that the contrastive loss is a better metric to use than using both, right? Using both metrics. So am I saying that the researchers are wrong? No, they are not definitely wrong. There can be a number of reasons for the contradictions. The first is the training itself. The authors used nearly 5,000 videos for training and nearly 1,000 videos for testing, whereas I use 50 videos for training and only 20 videos for testing. So due to the lack of training, it can be the case that my model didn't have enough features to learn, and as a result, it could not classify some videos. More training would mean more features to learn, and so high chance of the area under curve to go down when both loss metrics are used. So if we have more features, we'll learn more. If we do more training, we will learn more features, and so the chances of distinguishing between fake and real would go higher. And the contrastive loss only appears better. It may only appear better because all the training and testing videos that I used had both modalities present. So it could always extract the loss value, and as I said before, it always guarantees a classification. So and so it will provide a better distinguishability. So it comes down to the question that why did I not train more? The reason is because of collab limitations. If I'm using more than 50 videos, or yeah, more than 50 videos, it tends to crash and it revokes access to the GPU runtime, which is crucial to do the pre-processing, right? And so and another reason is that the key aim of the paper is to use the audio and video modalities to do deepfake detection. And if you think about it, the contrastive loss itself represents this approach, right? The reason they have the contrast the novel approach comes in the form of the contrastive loss, and the fact that the graph from the model using contrastive loss only performs better is proof that the model is still good enough for detection when dual modalities are present, right? So in other words, the key concept for detecting videos using the dissimilarity in modalities is still valid, is still working just as fine as the authors claimed. So in conclusion, the technique provides a novel use of existing methods such as face and scene detection and speech recognition by applying them on different modalities in deepfake detection. Other than just detection, it also provides a second application, which is to pinpoint which parts of a video are most likely manipulated. So it's not just detection; it has a second function to it, which would let anyone sort of investigate which parts of a deep fake was manipulated. So it has more utility than other detection methods that only do detection. So that is the end of my presentation. Thank you for listening, and thank you for reaching the end of this presentation. Thank you.